All- So again, these are the problems, and yeah, let's start the lecture. So this is my rough plan for today. Uh, we will try to cover as much of it as we can and do some problems along the way. So, so everyone here knows what a vector is. So from physics, and so at least in physics, the notion of a vector is you have the axis, and a vector is a sort of a directed line segment. And given two vectors, you can add them by the triangle law, and so that will be our physical intuition for vectors, and we will be jumping around through the physical intuition and the mathematician's way of looking at. So for us, a vector is anything that can be added to other vectors and that can be scaled. So these are the two basic properties we will require. That is, if we have to have a vector v and a vector w, we can define their addition v plus w. And if we have a vector v, then given any real number, so we can also take rational numbers, any field works, but for now we can scale it by, let's say I can scale it by root 2 or something, and that will just elongate the vector by amount to 2. Right. So that's a vector, and so a vector space is a set of vectors closed under addition and scalar multiplication. So yeah, so my handwriting is legible, right? Someone, or is it too short, too big?
Yeah, it's visible.
All right. So a vector space is a set of vectors closed under addition and scalar multiplication. And examples. So the real line, which is and so here the vectors are real numbers and addition and scalar multiplication is defined the usual way. Another basic case is R2, in which we traditionally represent R2 by a pair of orthogonal axes or axes at 90 degrees, but you will soon see that it's not really required for them to be at 90 degrees, or there are a bunch of things we assume too much of. So in R2, the vectors are so there's a subtle point, but we will assume that all the vectors start at origin, right? And if we have two vectors, we want to add them. For a second, we will assume that they might not start at origin and define their addition the way it's done in physics. Same in R3, we have uh, three space, and yeah, we can add scale vectors. So I guess all of you already have some idea of why these are vector spaces. So here's another example. Uh, let's say the set S, which is the set of all polynomials in R of X, with real with polynomials with real coefficients, and degree of p of x is, let's say, less than 5. So this looks like a plus bx plus cx square plus dx cube plus ex x 4. And to turn this into a vector space, we use a very powerful mathematical technique called forgetting. And we forget that we can sort of multiply polynomials. Right? So given two polynomials, we can define their addition the usual way, and we can also define what it means to multiply a polynomial by a real number. Right. So another example, let's say the set uh, S, which is the space of all functions from anything works, but okay, 0, 1 to R, right? Given given two functions, we can define their addition. This is just pointwise addition and scalar multiplication. Yeah. So everything so far makes sense, right? That everything is a vector space. We can add and we can multiply the scalars. So let's see a few more examples and a few non-examples. So all right. So I hope you can see the writing. So Z2, which is Z cross Z, and we scale it by elements of Z. Can someone tell me if this is a vector space or not? Right. So let me actually. So is the definition of a vector space clear for everyone? You can type a yes in the chat or say a yes. All right, I'll wait for one more yes and a few more yeses and then. So anyone who yeah, someone was saying, anyone who wants me to explain what a vector space is, feel free to do that because I have really gone through the definition quite fast. So all right, so I'll give a sort of a brief overview again. So uh, yeah, so what does so vector space is essentially a set S along with a set of scales, right? So these are the constants by which we can multiply, and these are the actual set of vectors. So in the first example, we have, let me, not that, just a second. Yeah. So here the set is a comma b, a, b are in integers. So this is our set of vectors, and z is our set of scales. Right. So now can someone tell me if this is a vector space?
Yes.
Right. So this is actually, yeah, someone else is speaking.
Could you repeat the question?
So is the set of pair of integers. Uh, so our set of vectors is pair of integers, and our scalars, the things we multiply by, is the set of uh, S is the set of two tuples, and Z is the usual integers.
Yeah, this is a vector space.
Right. So there's a point I went ahead by. This is not a vector space, which is because this is not a field. That is to say that uh, you see, I cannot. If I have V, then I can get two V. I can go from here to here by multiplying by 2, but I cannot go back, right?
But
Because,
we can only multiply by scalar, not divide, right?
yeah, but see, the thing is ideally, so we want so we want to be also able to go back from 2V to V. And why this is a good thing, it will make sense after a bit, but yeah. So we also want half to be a scalar, right? So we are not actually multiplying, but we are actually not dividing by a scalar, but we are multiplying by the universal thing, right? So, right. So since Z is not a field, that is, we cannot divide. A field is a place when you can add, subtract, multiply, and divide. Since Z is not a field, this is not a vector. Right. For the second one, not that. Let's say the set of all real sequences. Is this a vector space?
Yes,
Right. And what is the underlying field?
the reals.
Yeah. All right. Well, let's go on to the next one. Q of root 2. This, if you have read some napkin or some as fancy algebraic number theory stuff, then this will be very familiar set. This is the space of all elements of A plus B, when A and B are rational numbers. So is this a Q vector space?
Yeah.
Right. Is this a R vector space?
No.
Why not?
Because, for example, if we multiply a by a comma b by say root 3, then we no more get element of q root 2.
Yeah, exactly. Because multiplying by a random element of R, this thing does not belong in Q. Right. So again, notation. This just means space of all polynomials, and so our notation will be K will always replace a field. K will always mean some random field. It can be Q, it can be R, it can be Q root 2. We will see that Q root 2 is also a field. But alright, so few more. So someone quickly tell me if 5 is a vector space. So 1, 4, 6, 7.
Uh, 5 is
So
with, you are asking 5 with respect to what? Like r or what?
yeah, R.
Oh.
Not a vector space.
Why?
Because, uh, Yes, this is a vector space.
Yeah, this is a vector space, right? Because if f and g are continuous, then so is sorry about that. Wait, yeah, then so is f plus g and cf for any c belonging to R. So this is a vector space. Uh, Here, so the complex numbers. I mean, these are just bunch of examples. So anyone can unmute and just quickly tell me all of them.
Could you repeat?
So I'm just asking if the sixth one is a vector space.
Uh, what is the first thing you have written?
This is complex numbers.
No, the first thing on the right.
Uh, Q rationals.
Oh, yeah, it is a vector space over everything.
Yeah, over all of them. Yes. Okay, we will come back to this one later. This also later. This one. So wait, what happened? Right. Problem 9.
Yeah, it is
So what do we
also
have?
a vector space.
Yeah. So the thing you have to check is if f1, f2 are solutions, then so is f1 plus f2 and cf1 for any c in R. Now this. Have any of you seen the Cauchy functional equation?
Yeah,
Right. So can you tell me what the equation is?
f of x basically additive. F of x plus f of y equal to f of x plus y.
So somehow this question and the solution to this functional equation are related, but we will come to that later in the talk. So is the reals a Q space?
Yeah,
It is. All right. Let's go to the last example. Just a second. Is this line a vector space under reals? So by line I mean points on the line.
I think if and only if the line passes through the origin.
Yeah, exactly. If and only if line passes through. Or nice. So all right, let's move on. Actually doing something. Uh, I'll do this. Yeah. So right. Uh, so suppose I have the okay definition. Definition given a vector space B over let's say R, a subset W of V is called a subspace if W is itself a vector space. Just like very sort of dumb definition, but so suppose all right, I have the R2 and a vector, let's say this vector uh, 1, 5. What is the smallest vector space? I'll call this V that contains V.
The line passing through region and the point 1 comma 5.
The line passes. Alright, so which is to say that the answer of this is we will denote it by this. This is the space of all CV where C is in R. And pictorially, it looks like this line. Not that line. That. Let me move it. Yeah, this line. Alright, so you see, so this is a very natural thing to ask, and in general, given a set of vectors S, let this be the notation denote the smallest uh, vector space that contains S. Right. So uh, yeah. So suppose V is 1 comma 5 and W is let's say 2 comma 3. What is this? Here's the picture.
The set of all C1V plus C2W for any constant C1, C2 in R.
Exactly. Very good. This is C1V plus C2W for C1, C2 in R. But can you tell me a more explicit form of this? So everything so far makes sense, right? Anything anyone wants me to go over again?
Yeah, this is in fact the whole set of points in the plane.
Exactly. So that's the idea, right? That somehow just two vectors are able to populate the whole space because you see, given any random vector, I can write it as a sum of a multiple of V and a multiple of W, right? So can someone actually tell me a breakdown of this? Given a random point of R2, what are the constants C1 and C2? The question is clear, right?
And so like you just solve the equation C1 plus 2C2 equal to X and
Yeah,
5C1 plus 3C2 equal to Y.
right. And these are two linear equations in two variables. You can either, if you don't believe this can solve, you can for now believe me that this can be solved uniquely. And also the thing is here C1 and C2 are unique. This might not be the case always. So, okay, another example. So for people who already know, you can try the problems which I gave. For people who already know the theory, you can try the problems I gave at start of the talk. And if you miss them, you can just ask me and I'll show the problems. So intuitively, R2 has dimension 2, right? And somehow that connects to the point that R2 can be spanned by two vectors. But suppose V and W are R2, is it always true that is this equation always true?
This is true if and only if V by W is not a real number.
Yeah, exactly. V and W are scalar multiples of each other. This is only true. So first thing is VW are non-zero, and two. So the thing you said, there is another way to say this, right? Implies C1 equals C2. There is only one way to get to zero, right? Does this make sense?
Yeah.
Okay. So definition. So I already defined the span. So okay, let me actually give an example of what goes wrong. Let's take V equal to 1 comma 2 and W equal to, let's say, 2 comma 4. Then V comma W looks like C1V plus C2W, which is C1 plus 2C2 comma 2C1 plus 4C2, and this is just a constant times V, right? Which is why this thing is same as this, and so on. So something goes wrong when we have multiples, right? When the vectors are multiples of each other, and we want to sort of make this notion precise. So before that, let me actually go to R3. Is I need another name. Let's say U. When does this not happen? I mean, when does when is this equation true?
This is true if and only if U, V, W are linearly independent. Basically, that C1,
Yeah,
C2, C3 equation will hold if and
yeah,
only if
exactly,
all are zero.
exactly. So here, in the R2 case, V and W, one of them would have to be a multiple of the other, but that's not true here. So, for example, let's say 101, W is 203, and U is 001. So, what does this look like?
XY plane. XZ plane.
Is it the exact plane? Probably, yeah. Yeah, Y is 0 everywhere, right? Yeah. So, this looks like A comma 0 comma B in general. Yeah. So, definition. Let me given a set S of V, we say that S is linearly independent if and only if C1 S1 plus C2 S2 plus Cn Sn equal to 0 happens only when all of them are equal to 0 themselves. And otherwise, we call as linearly dependent. So, is so we sort of have a uh, suppose S spans R power n, then can someone tell me an inequality on the size of S?
Greater than equal to n?
Yeah. And if S belongs to R power n is linearly independent, that implies what? That implies this is less than equal to n, right? So the idea is that if we pick more than n vectors in Rn, they will be linearly dependent. So, so now we want to define definition basis. So we already know that let's say the if S spans V, then mod of S is what is greater than equal to sort of the dimension of V, and if S is linearly independent, then mod S is less than equal to the dimension of V, whatever intuitive notion we have of dimension. So here we formalize the definition. Set S of V is called a basis if S spans V and S is linearly independent. Now dimension is equal to size of basis. Right. Everything clear so far? Because I think so far everything has been very intuitive. Anyone who wants me to explain the definition or anything?
If the span is the whole vector space, then I mean, if S is linearly independent, then obviously the span is the whole vector space. No?
No, because let's say you are in R3 and this is the span of S is not R3, right?
Oh, oh, right. Okay.
So if you, so we have linearly independent subsets and we have generating subsets and their intersection is all sets which form a basis. Right. I'll just wait 30 seconds if anyone wants to ask me, anyone wants to ask me anything, because I think everything so far has been sort of very intuitive, and we will move on to the problems in a bit. So yeah, feel free to ask me, even if you want to ask something, let's say, something simple. Feel free to do that.
Can you please explain how R is a vector space over Q?
Right. So yeah. So nothing on this page, right? Because I will move on to the problems now. All right. Yeah. So before going to that, I will actually try to answer a few more problems to give you some intuition. Right. Uh, should I, yeah, let this stay. I'll use it. So this color is visible, right?
Yeah.
Yes.
and you can differentiate it from both yellow and both blue and red.
Yes.
Alright. So, what is the dimension of this?
One.
Is it one?
Infinite.
So, you can see the question, right? I want uh, maybe the page is very. I'll move it around a bit. All right. So I want q root 2 as a q space. What is the dimension? Why is it one? I mean, the person sells name.
I think
Can,
it's 2.
This is 2.
yeah, dimension is 2, right? And can someone tell me a basis?
1 comma root 2.
1 comma root 2. Okay. So in general, the basis can be anything. But I mean, there are many possible options of for choice of basis. Even 2 comma let's say 1 plus root 2 also works. But intuitively, or at least the dimension is 2, right? Because any one element set cannot span this, and a two element set does span this. All right. Okay, let's do this. What is the dimension of this?
Infinite.
That is correct, but so can someone give me a basis?
Like 1000, then 01000, then 00100, and so on.
So sequences which are one at some point and zero at everything else, right?
Yeah.
Is this a basis? Is this a basis?
Yeah, I think. Yeah.
So here's the technicality. This is not a basis because you see, let's say I cannot express this element as a finite sum of these, right? Basis by definition, span by definition can be a finite sum. Did that make sense? It's just a small technicality, and we won't be dealing
Could
with.
you repeat?
So this is not a basis because this thing, this element of this sequence, which is the constant one, is not in its span, right? Because span can only contain finite sums.
Oh.
So yeah, the dimension is infinite, but this is not the basis. In fact, you can show that the dimension is uncountably infinite.
But in reals also the dimension is uncountably infinite.
Yeah.
So why don't we have the same problem there?
So I don't understand the question. Do you mean R as a R space?
R as a Q space.
R as a Q. So yeah. So R as a Q space has uncountable dimension.
So
The
does this sequence even have a basis you mentioned?
so yeah. So that is a question, right? So the thing is when dealing with this infinite and especially uncountably infinite things, it's a lot of technical things come up, and I won't go into that today. But if you want to look it up, you can look up these words, and hopefully at least one of them will lead you to an answer. All right. You can
So we should search
Google on.
this on net and we'll get eventually our answer.
Yeah, but it is. I mean, it's not interesting. At least it's not interesting to most people. It's just uh, uh, it's just a bunch of technical details, and we won't be talking about infinite spaces, infinite dimensions, which is too much anyway. Right.
Wait, why does why is that 1 1 1 1 1 not a reachable vector? Because we add
Because
all of these uncountably infinite terms, then
this is countably infinite, right? This set is countably infinite,
yeah, yeah.
but the span only allows finite sums.
Oh, okay.
You
So
see,
so we have to use, so in these proofs which they give, I don't know them. They will prove that we can use finite sums to describe of a basis to describe each element.
yeah, exactly.
Okay.
So since this seems to be of interest, let me give you a bit more indication about why this does not span. Uh, my screen is stuck. Oh, okay, it's clear now. A lot of things have juggled up, but okay. So let me call EI the sequence which has 1 at the ith place and 0 everywhere else, right? Then we have S, which is E1, E2, dot dot. Can you tell me? Can you tell me a space W which is not all sequences, but W contains S? Is the question clear?
No, could you repeat? Like, could you explain
So can you
again?
can you give me a uh, can you give me a vector? Can you give me a subspace, a proper subspace of this space which contains S? S is our proposed basis.
Yeah, I think we can take W to be the set of all such sequences, but with the extra condition that uh, that uh, that the number of non-zero elements is finite.
Yeah, exactly. All sequences, but zero after a point. It is sequences which are eventually zero, right? So this is a space which contains S,
No, I
but
meant
is not.
like zero can be at the starting everywhere, but at the end we have finite numbers or something.
Yeah, so I'm saying that you have a bunch of numbers, but after a point, it's all zeros.
Actually, I
Can begin.
didn't. I can't get what you mean. Like, are you saying that the point after which it is zero is fixed, or is it not fixed?
It's not. It's not fixed. I mean, the sequence eventually zero sequences. Is
Oh,
what I'm
got
saying.
it.
So it can be after 1,000 steps. It can be after 1,000,000 steps, but after a while, it is zero, right? And so this is actually the span of S, and this is a proper. This is a proper subspace of V, right? So hopefully that gave you some intuition. And so polynomials as a case space. This has a. Can someone tell me a basis for this?
For which?
I have polynomials with coefficients in k, and k is a field. So you can take Rx as a space.
We can have 1
Yeah,
x, x square, x cube, and so on.
yeah, exactly. This is a basis, right? And you can
Yeah.
show that any basis is. So you see the difference between this problem and the sequences, right? What do I do? So this is kx is sort of the coefficients are zero after a while, right? So you get a nice correlation between this problem and the sequence problem. And if I want a version which is sort of all sequences, then I can take this, which is of this form here, I think, formal series, or people you might know it as a generating function, and this is infinitely going on, right? This is not a basis by the same argument. All right. These is C is a Q space. Dimension, same thing, right? Uncountably infinite. As a R space,
2.
2.
2. Right. As a Q root 2 space, also it's uncountably infinite. And okay, the linear maps we will go to later, but can someone tell me the for problem 9, what is the dimension? I mean, figuring out the dimension is one of the ways to actually solve this functional equation. So the dimension is actually, I think, if I remember correctly, I think it was 6, and you can find this problem in Ivan's monster if he handled. I think that was the name.
I I joined the class late, so can you please explain how is the dimension of a functional equation 6?
Right. So if so, the thing is the space of solutions of the functional equation is a vector space, right? Because if we have two solutions, then we can add them, and that will also be a solution, and CF1 will also be a solution. I mean, it will require you some verification, but those are minor. That is clear, right?
Okay. Okay.
So the solution space is a vector space. And that is why it makes sense to ask what the dimension of this space is.
Yeah. Yeah, got it.
Interesting.
Solution is a vector space. Then
So here's another. Yeah. So one of the ways of kind of getting an intuition for solving this problem is to figure out what the dimension of this is, and the dimension of this is actually 6, but uh, it's a rather famous problem. You can check it out in Ivan's monster handout, and he
no,
explains why.
I was asking how do we get the dimension equal 6?
Yeah, that's the hard part, right? That is hard because I mean the problem itself is hard. So asking the figuring out the dimension is also hard. This has a solution, but I won't talk about the solution now because
Okay.
yeah, it's a bit tricky. So another example of a FE which has a vector solution. I think you can correct me if I'm wrong. I think 2018 FI this was all the solutions were of the form AX plus B by X. Can someone does someone remember the problem?
Yeah, it was 2018 A5 only.
Yeah, can you tell me the statement, the functional
Uh,
equation?
just a second. Um, it was x plus 1 by x into f of y equal to f of x plus y plus f of y by x. I'll also type it in the chat, though it will not get
Yeah,
latent. Y by x.
yeah. Thanks. So quite often, F is the solution space of the F is a vector space, and it sometimes helps to get the dimension because yeah, it gives you a way to. Sometimes it gives you more intuition to, or gives you a way to solve the problem. Yeah, this is on linear algebra. This problem.
I was asking how do we get the dimension of a functional equation? So, can you explain that with some other example? I mean, not these two problems, as you say, they are famous. And would like to try.
Right. So getting the dimension actually in most cases solves the entire problem. So let me think of an example. Uh, okay, I don't have an easy example. So the thing is, right. So let me talk about one of the ways this problem can be solved, and hopefully that will give you some idea. So once you figure out that the dimension is 2, and you conjecture that all solutions look like this, you can somehow, so here's the thing, right? If fx equal to ax plus b by x, then what are a and b in terms of f? Can someone tell me?
Basically, we can look at what is F1 and F2 and just solve the system of
Yeah.
equations.
So some combination of f1 f2. This is also some combination of f1 f2, right? So the idea then often is that you try to show that the function fx minus this combination times x minus this combination times 1 by x is equal to 0. That is, so did that make sense? You
Yes.
guess what A and B should look like, and then you try to show that this thing is identically 0.
Yeah, got it. Got it.
Last example before we go on to better problems. Oh, I actually don't have much time. Alright, so R is a Q space, again uncountably infinite, and you see this, there's a hidden condition here, right? You can prove that f of Rx equal to Rf of x for R in Q. So this essentially is a linear map on Q space. So I'll tell you what a map looks like. Let me. I think I have a nice video. Uh, so these are what maps look. A general linear map looks like this. So you kind of see the structure, right? You have two vectors I and j, the usual I and j, and you sort of move both of them to some place, and that somehow moves the whole of your grid, right? Let me show
I
you
didn't
how.
get this.
Right. So at least, I mean, formally it might not make sense, but the picture makes sense, right? What we are trying to do. So the green one is the I vector, the red one is the j vector, and
Uh,
this is what a general linear map looks like. Yeah.
we are
Yes.
rotating, right?
Yeah.
But the angle between the red and green vector has changed.
No, but we are not actually rotating. We are rotating. We are kind of sharing it out.
Could you repeat?
So yeah, the angle can change, right? Because okay, where's my? Maybe I actually need to take. Yeah. So all right. Uh, definition linear map. Given vector spaces V to W, a linear map is a function which has the properties that f of v1 plus v2 is equal to f of v1 plus f of v2, and f of lambda v1 is equal to lambda times f of v1. Right? This is what is called the linear map. This is fine, right? This is clear. This is the
Yeah.
formal definition. So if I want to specify a linear map R2 to R2, I can just tell where I goes and where j goes, right? That would essentially determine the whole plane. Ij are the unit vectors, or if you prefer the mathematical notation.
Yeah.
So let me take another color. I can send I to some place here, and let's say j to some other place, and this will sort of determine the linear method. Are you getting what I'm trying to say?
Yeah.
So yeah, this is what the so this is a linear method. This thing. A few more examples. Here you should scale both of them, and so these are just to give you some for people who have not seen what linear maps look like. The pictorial representation. This is a rotation.
Could
Uh,
you show that video again where the map is a bit weird? The first video you showed.
so the thing is, I can send I to any vector and j to any vector, right? And that will give me a unique linear map.
Oh.
I don't need to sort of preserve the angles.
Mm. I didn't get why these blue lines look like this. For example, one of the blue lines is parallel to the green one, but the other blue line is not parallel to the yellow one.
So the yellow one is a random vector. The yellow one is not j vector, right? The yellow one is a random vector. The green and red are your bases,
Oh,
right? Is this clear?
yeah, got it now.
Like another example. This is called the flip. So you map I to j and j to I, and the whole image gets flipped. Uh, okay, that I can actually get to that a bit later. Ah, all right. This is clear. What more can I talk about? Define the linear transformation basis. Change of basis. I don't think I have time to do change of basis. But okay, let me actually try. So a general linear map, let's say R2 to R2, sends 1, 0 to let's say A comma B, and 0 comma 1 to C comma D. And where does xy go under this map?
X bracket में a plus b plus y bracket में c plus d. Oh, sorry, c comma d and a comma b.
Yeah, x times A comma B plus y times C comma D, which is ax plus cy and bx plus by. And I can sort of represent this as a matrix, right? The first column would be image of 1, 0, and the second column would be image of 0, 1. This is AB, CD, and then I can define matrix multiplication the usual way, and stuff works out. AB times this. Wait, actually, stuff does not work with it. Wait. Alright, this is not this B. So this is CY. This is BX. CY. So linear maps are same as matrices. Is that clear?
Clear.
Alright, so let me actually move on to the list one interesting problem. Okay, let's try the first one. So was anyone able to solve the first one? Right. So
Could you give like 2-3 minutes more just for this problem?
yeah, sure. Take it in. The problem statement is clear, right? Let me zoom a bit.
Yeah, it's clear.
So just some extra information. This is called idempotent map,
Oh
or
yeah,
and
so I can
I,
prove that every element can be represented as like a sum of a plus b with a in v naught and b in v1.
and uniquely.
That I'm trying.
So I was saying that any map that satisfies this condition is called idempotent map, and this is a very important condition. This comes up a lot, and a more familiar name, I guess, is a projection map. So exercise makes sure that
Yeah, I
your
got uniquely also.
yeah, just a second. Intuitive idea, not that idea of a projection satisfies P of P is equal to P. Yeah, uh, tell me a proof. Some
Basically, you can write x as p of x plus x minus p of x
uh, sorry, P of X.
plus x minus p of x. Like x minus p of x is in bracket.
All right. So this is in V0. This is in V1. And can you prove that this is unique?
Yeah, like if you, it suffices to show that the only way to represent 0 is 0 plus 0, and you can like take f on both sides. For example, suppose 0 is a plus b with f of a 0 and f of b b. Then if you take like f on both sides, then you get that f of b is equal to 0. But we know that f of b is b. So b is equal to 0 and consequently a equals 0. Oh, it was B. I messed up. Like,
Yeah, that's right. So another way is to pick a V, and suppose V is of the form x plus 1, right? And this is in V naught, this is in V1. Then what is P of V? P of V is this goes to 0 and this goes to y. This gives you a linear equation, right?
yeah.
This gives you a linear equation, and you can solve for y in terms of b and pv and same for x. All right, good. So the next one is also similar. Uh, I'll give you a few minutes to try.
Yeah, so this is also similar. You can write x like v as v plus fv by 2 plus v minus fv by 2.
All right. Uh, Same. Now, if you notice something, this kind of looks like the polynomial x square minus x, and this looks like the polynomial x square minus 1, right?
I didn't get this.
So the first equation we had p of p minus p equal to 0, and the second one we have this was p1, and p2 was t of t minus 1 equal to 0, right? This looks like x square minus x.
Why
This
is
looks
t
like
of t minus 1 equals 0? Like t of t of x minus x was 0.
the identity.
Oh, yeah, got it.
So I'll leave it to you to generalize. Uh, I won't do it now, but I'll give you. So yeah, this is. You can try it later, and if you get stuck or if you have any problems, you can ask me in Discord. Actually, okay, I have one more interesting one. Actually, quite a few more interesting ones, but okay, let's try this one.
What do we have to generalize?
So I actually. So the first problem was about this polynomial. The second one was about this polynomial. So yeah, generalize how much you can. Maybe first try. I mean, the question is clear, right? You can maybe try for x power n minus 1 and maybe a general irreducible polynomial, which one works, which one doesn't. Yeah. So it's clear what I mean by generalized.
Yes.
Or
Yeah, we'll try on our own and see what works.
yeah, yeah. All right. Problem 5. So has anyone seen problem 5 before? I hope not.
Yeah.
At least. Nice. So this is actually some old book now. I think 2000 something. But yeah. So for people who have not seen, I'll give you. A, this is sort of a hit or miss problem, at least for now. But yeah, I'll give you a few minutes to try the problem.
A and B differ by a constant factor. I think. I mean, constant addition.
And why do you think that?
I mean, one. I mean, a of x is c is p times b of x plus q. I mean, you multiply and add something. I think that because you put y equals 0, then c of y is a constant, c of 0 is a constant, d of 0 is a constant. So 1 equals a of x times constant plus b of x times constant for all x, which means it's an identity.
Nice.
So if I'm forced to think in linear algebra terms, then I will say b of x is uh, what has span a and some constant, but I don't really know.
Yeah, we are almost at the point, and yeah, I think with a few more minutes we will get anyway. So I'll tell you the proof. I'll actually tell you only the idea. So idea: put in some values of y, LHS, RHS is not his, but looks like span of AX and BX. So dimension less than equal to 2, and idea is to show that for some values of y, uh, LHS can have dimension. Not this is not properly. So right. So the idea is that you put in a value of y. Let me call it p of x comma y. The idea is that to show that p of x comma y1 and p of x comma y2, let's say, and x comma y3 is linearly independent for some values of y1, y2, y3, and this will tell you that this has dimension greater than
Dimension
3.
3 because 1 omega and omega square are roots of it. So they are linearly
Uh,
independent.
but I'm only looking at, so the thing is, so I'm looking at it as a, so what you are doing is you are looking at r of x comma y as a vector space and arguing that, I mean, it will work out, but for the details, the dimension 2 over r of x, since I'm already fixing a y, and here also I'm in the same thing. But yeah, I mean, the idea is clear and it will be easy to solve. Okay, I have 14 more minutes, right? Okay.
I guess you can go a little above that. And usually 5-10 minutes off. Yeah, that's it, but I
All
don't.
right. I'll try to motivate change of basis and we will end here. And if you want another session on this, you can write that in the feedback and I'll try to do that. So, okay, change of basis, motivation. So, suppose I have given you the map, let's say this one. Can you tell me what A power n is? No, right,
Can
because this is somewhat hard. you will have to do induction or something you'll have to do. But it is for a 2 cross 2 matrix. And if I give you a general n cross n matrix, it is a hard problem to find out what a bar n looks like. But if the matrix has a special form, not that color. So suppose the matrix looks like this. Then you can quickly tell me what this is like. Someone?
2 to the power n and 3 to the power n.
Right. So the point is that here E1, so I will denote the standard basis vectors by E1, E2. E1 goes to 2E1 and E2 goes to 3E2. And this is, I can easily tell you this is after one application, and I can easily tell you what it looks like after an application. This is 2 power n E1 and this is 3 power n E2. But for the other one, I have this matrix. E1, where does E1 go to? Someone?
2e1 plus e2.
And E2 goes to 2E2. Actually, let me write E1 plus 2E2. And this is sort of hard to tell what it looks like after endpoints. But can you find me some combination of this? Let's say lambda 1 E1, not lambda. Let me pick a better constant. Let's say AE1 plus BE2 such that after the map it looks like this. Find AB lambda.
A is applied only one times or n times?
Just once. So the thing is, uh, I want a combination which gets multiplied by a constant. So it's not even clear if AB exists, right? This is not clear if such AB exists, but let's assume they exist and let's try to find them. So say 2112 times AB is equal to lambda AB. Now can someone tell me one example of one a triple which works?
One one three.
Yeah, 113 and another with something other than 3.
One negative one one.
Yeah, 1 negative 1 1. So E1 let's mention this E1 plus E2 goes to 3 times E1 plus E2 and E1 minus E2 goes to E1 minus E2. So here's the idea, right? Initially we had V in R2 and we were expressing it as some combination of E1 and E2, and then AV A power n V is hard to find. But suppose V was rather some combination of these two things, then can someone tell me what this looks like?
C times 3 to the power n.
Yeah, 3 power n C1 plus C2 plus D V1 minus C2, right? So the thing is, which basis we pick actually matters, right? So here E1 plus E2, comma E1 minus E2 is a better basis than the standard E1 comma E2.
How can we show in general that E1 plus E2 and E1 minus E2 will form a basis? I mean, like the two vectors which get multiplied by constant, they can be like linearly dependent also, right?
Right, exactly. So if this forms whether some combination forms a basis or not is a hard problem, but yeah, so there are ways to do that, but like a basic ways. So for at least for R2, you can just see that they are not linearly independent because they are not multiple sufficient, right? But
Yeah.
in general, it's hard. Actually, it's not that hard, but it's hard to find, hard to check whether this is a basis. So, uh, okay, I'll probably have to go on 5-10 minutes more, but goal to show that the matrices A and SAS inverse are essentially the same. Here's some motivation. So suppose I have a permutation, right? Let's say of this, and let's say one goes to here, two goes to itself, and this is sigma, and I have another, let's say sigma dash, A goes to C, B goes to B, and C goes to A. Then sigma and sigma dash are essentially the same permutation, right? Does that make sense intuitively?
Yeah.
So how to formalize this? So in general, let's say sigma is a map from S to S, and sigma dash is a map from T to T. And what we are looking for is a bijection F from S to T such that A goes to, so sigma takes A to sigma of A, and sigma sigma dash, so A is not a good, X goes to sigma of X, and the image of it, this is in S, the image under F, which is F of X, sigma dash takes F of X to F of sigma of X, right? So, which is to say that, how do I say this in one word? So, I'll just tell you what our example looks like, and I'll leave it to you to make sense. Sigma was 1 goes to 3, 2 goes to 2, 3 goes to 1, and sigma dash was A goes to C, B goes to B, and C goes to A. What's the F that works? So this is
F
our
will send 1 to A, 3 to C, and 2 to B.
yeah exactly. Uh, right. So F sorry sigma dash takes f of x to f of sigma of x, right? So sigma takes x to sigma of x. Sigma dash takes f of x, the image of this, to the image of this. That is the essential idea, right? Of why these two maps are the same.
Yeah,
So this diagram makes sense, right? This diagram that I have drawn.
yeah.
So so here's the general idea. I have S to S, a map called sigma, and bijection F is a bijection such that so here's the idea, right? There are two ways to go from S to T. One is this, and the other one is this. We want the two ways to lead to the same thing, such that so this way f of sigma of s is equal to sigma dash of f of s for all s in T. Sorry, for all s in S. Does this make sense?
Yeah,
So this thing in general is called a commutative diagram. Uh, and uh, these pop up very often in higher math. And a lot of the things you have been doing, so let's say additive functions. Additive functions, image of sum is sum of image, and there are many such things, right? Let's say image of product is product of image. So I'm talking about
are
the
you writing something?
you can't see it later.
Yeah, we can't see. Oh, now we can.
Yeah. Okay. So you have already seen. So the thing notice here is that these two operations commute, right? The order does not matter. So your whole life you have actually seen quite a bunch of commutative diagrams. That is two operations which order does not matter. So this is a very natural thing, right? Did that make sense?
I still didn't get why additive and multiplication function relate to the commutative diagram.
Right. So you have two operations, right? Taking the image and taking the sum, and these two commute.
Yeah,
And here, the image and the product commute. So you have two operations that commute, right? And whenever that happens, you can write that in a commutative diagram. What did we have here? We have operation sigma, operation f, and it commutes with f and sigma dash. So that is uh, f of sigma is same as sigma dash of f.
but in the commutative diagram, there were four functions, right?
We had three functions, but I mean, we can take the special case where t is actually equal to s. We are kind of generalizing the idea of commutative, but okay, right?
Got it.
So let's say I'll give you an example. S to S, sigma takes 1 to 3, 2 to 1. Actually, let me do 2 to 2 and 3 to 1. And let's say f is the function h to s such that 1 goes to 3, and actually that's a bad example, but okay, let me, yeah, this is fine. 1 goes to 3, 3 goes to 1, 2 goes to 2, 4 goes to 4. Then f of sigma is same as sigma of f, right?
I mean, aren't f and sigma just the same function?
Yeah, they are. So I have to actually get a better example. Okay, let me do this. 1 goes to 2, 2 goes to 3, and 3 goes to 1.
Actually, in the
And f,
commutative diagram, there were a function sigma dash also.
yeah, so here sigma and sigma dash are the same. I mean, you can also take, it does not really matter, but okay, how do I properly explain this? Um, yeah, okay, let me do this. The thing is, if we relabel 1 as 3 and 3 as 1, sigma does not, uh, how to explain this, how to explain this? So, do you guys know what a permutation cycle is?
Could you repeat?
A permutation cycle?
Yeah, yeah.
Alright, so that will be the best way to explain. So, let me type sigma in permutation form. 1 goes to 2, 2 goes to 3, and 3 goes to 1. So, this is sigma, right? And
Yeah.
suppose we have another map tau, which is also of this form, but let's say 1, 4, 2, and 3. Then sigma and tau are same after one relabeling, right? They essentially have the same structure, a 3 cycle and a 1 cycle.
And what's the relabeling?
Uh, 1 goes to 1, 2 goes to 4, 3 goes to 2, and 4 goes to 3. I mean, just these. They have the same structure. That is, if I have any property about sigma, that is, let's say sigma cube equal to 1, then tau cube would also be 1. So the way sigma acts on 2, tau acts the same way on 4, and the way sigma acts on 3, tau acts the same way on 2, and so on.
What do you mean by one relabeling? We are relabeling three numbers here.
Yeah, by one relabeling, I essentially mean a bijection from. So the point I'm trying to say is that if sigma satisfies some property, let's say sigma q equals 1, then tau also satisfies the same property because these two permutations are structurally the same. They have the same structure.
Yeah.
So my point of doing all that was that I had the map A 2112. Suppose I have the map B 3001. This takes E1 to 2E1 plus E2, E2 to E1 plus 2E2, and this takes E1 to 3E1 and E2 to E2. But the point to notice is that A takes E1 plus E2 to 3 times E1 plus E2 and E1 minus E2 to so A and B. So A and B one can get from A to B by just a change of basis, right? That was my point. Maybe the permutation example was actually more confusing. So I'm saying that it makes sense to call the two matrices similar.
Yeah.
Yeah,
Yeah. So and the change of basis was actually the relabeling there, but okay, all right. So okay, let me end with the video. End with a video for the map. So you see, we have E1, E2, E1 plus E2, and E1 minus E2, and we will apply the map F. And you see, uh, both E1 and E2 have uh, they are not on what they are not on what their previous span was, but E1 plus E2 and E2 minus E2 are on their span, right? Did that make sense?
yeah.
Right. So uh, so by diagonal, I mean find a matrix which is similar and which is diagonal, because diagonal matrices are easier to compute. Yeah, that's it. Any questions?
By the way, is there any nice way to represent this similar relation is matrix from like will the matrix these 2 1 1 2 and 3 0 0 1 satisfy some good relation?
Yeah, so they are the same after one relabeling, right? So let's see. You can see my screen again.
Yeah.
So the thing is, we have V to VA and V to VB, and this will be a function f. F is the change of basis. F takes, I think, E1 to this and E2 to this. So f of A is same as B of f, which is to say B is same as f f A f inverse. And in general, if you have a matrix A and B such that B is equal to T A T inverse for some matrix T, then A B are similar.
And
right?
can we always choose T such that B has a non-zero elements only on its diagonals?
Right. So the question you're asking is, given a general A, can we find T such that T inverse is diagonal, right?
Yeah.
So the answer is sadly no, and try this one. So E1 goes to E1 and E2 goes to E1 plus E2. We cannot. Yeah. I hope you have written the gum and yeah. Anything else?
So can you find a good form of the maps which we can diagonalize and which we cannot?
Yeah, that takes quite some theory. So I'll give you a few references. I think napkin covers that the best. Uh, can you see my references screen?
No. Yeah, now it is. No. So practically it might be a bit tough to read all of this. So which one would you recommend?
I mean, anything works. I think uh, this is fine if you want just the. This
Are
will
you
have
sure
most
whether
ideas.
napkin? Are you sure whether napkin covers all this? Because I've
Yeah,
read a bit.
napkin covers much more than what I said today. But yeah, exactly right. It does not go into too much detail, right? And for that, you can either read this book. This is sort of a more standard text, and if you want some more harder problems, then you can take this one.
Okay.
So I'll recommend read the part from napkin, and then if you want more exercises to do or more details, then you can read this book. He also has a YouTube channel with lectures on linear algebra. You can just Google session Sheldon Acker. Yeah. All
Should
right.
I end the recording there?
Yeah, sure. All right.